Question 7 wants us to describe how to go from cyclohexane, which is this, to cyclohexanol, which is this. So you don't know a way to do that in one step, and so it says to do it in 2 steps. So this is an example of what organic chemists call synthesis. Okay, the idea that you make something not necessarily, I mean it could be in a single step, but not necessarily in a single step, but that you need to be able to design a plan where you would do a sequence of reactions to lead you from one place to another. And synthesis is incredibly important in organic chemistry. I mean, it's the reason organic chemists have their jobs pretty much, you know, in industry and so on, because, you know, they take readily available starting materials and they turn them into valuable products by doing these reaction sequences. So in A-level you have to be able to come up with synthetic routes, but only in a very limited way. So normally they will only be, you know, a small number of steps, you know, maybe more than 2, but certainly not 37 in the way it might be in a sort of real life situation. Okay, so how are we going to get from here to there? Well, the starting point is to realise that you actually only know 2 reactions of alkanes, or in this case cycloalkanes. One is burning, and obviously that's not useful, but the other is radical substitution, that you can put a halogen atom into that ring by substituting for a hydrogen. So that has to be your way to go, because it's the only reaction you know. So the first step is going to be to do this, and you could put either chlorine or bromine in there. So I'll put bromine, but it really doesn't matter. And you need to remember how to do that. So the thing about these questions is you have to know your reactions really well, because that's harder than, you know, if you were asked, oh, what happens when you react this compound with bromine in the presence of UV light, which is how you do this. They ask you that, that's easy. But it's much harder when you have to think of using it. And the only way you're going to be able to do that is if you know your organic reactions really well. So if you haven't been trying to keep up and sort of memorize the reactions as you go along, hopefully you can see from this question that it's really important that you do that, because these kind of questions depend on you really having that readily available knowledge. So yeah, that's how you do it. The reaction is with bromine in the presence of UV light. Often in questions that will be all they want, but in this case it asked you to write an equation as well. So let's just do that. So remember, it's a substitution reaction. So when the bromine goes in, hydrogen has to come out, and what happens is that hydrogen combines with the other bromine from here, in effect, to give you HBr. Of course, that's not the mechanism, it's not as simple as that, as you know, but in terms of the equation, that's what you need to remember. So that's the equation for the first step. Okay, so that's all very well, but that's not the product we want, so we now need to have a method that takes us from here to here. But of course, there is one, because the reaction that you've learnt, and you've really only learnt one reaction so far for haloalkanes, is exactly that, substituting OH for your halogen in a hydrolysis reaction, or nucleophilic substitution reaction, whatever you want to call it. And the condition for that, remember, is that you use aqueous sodium hydroxide. It's very important to specify the aqueous there. It doesn't work if you just add solid sodium hydroxide. That's why it's called hydrolysis. Okay, hydro meaning water, so it depends on the water there. So aqueous sodium hydroxide is all you need for that. You might warm it gently, but you don't really need to put that detail in there, but that is what you need. And the equation for that is that plus NaOH gives you your product, which is what you want, cyclohexanol. And again, you can easily see what the other product will be, because the bromine's been kicked out, you've got the sodium there, so you've got sodium bromide as your other product. So that's the second equation. Okay, in question 8 then, we're starting now to look at reactions of alcohols. And the first couple, including the ones in this question, are ones that you already know about because they've come up as ways of making things we've already talked about. So this first one, heating an alcohol with concentrated sulfuric acid, you hopefully immediately recognised as the way that you use to make alkenes. Okay, so it's a dehydration reaction, elimination of water from an alcohol. So if you remember the general pattern for what happens in these reactions, what you have is two adjacent carbons in your molecule, one of which has the OH on board and the other one must have at least one hydrogen on board. And the idea is that you get an elimination reaction, which means that you just lose some of these atoms without adding any new ones in. And in this case, what you eliminate is that. So H and OH together will form water. And what they leave behind are obviously still these carbons joined together. But each of these carbons now only has 3 bonds, so of course that isn't going to work, and the way it gets around that problem is that it replaces these 2 bonds that are gone by forming a double bond there. And so you get the alkene like that. So you need to be very comfortable with that pattern of reaction. And then you need to apply it and realise that sometimes there's more than one way of doing that in a molecule. Okay, so let's look at this one. So this compound, it's drawn there in that sort of slightly strange way. If you want to, you can begin by redrawing that in a more familiar skeletal formula, but you don't have to do that. You can stick with this format if you want. And you can see what's going to happen is that this carbon is going to lose the OH, and then it's got a choice of 2 carbons from which the hydrogen can come to combine with the OH to form water. So your first thought might be, oh, that means you could get 2 different products depending on which of these carbons loses its hydrogen. But then because of the symmetry, you can see that actually it won't make any difference. If you lose a hydrogen from here, you'll get a double bond there. If you lose a hydrogen from here, you'll get a double bond there, but the product is the same thing in both cases. So the product will be propene plus water is the only possible outcome in that case. So here, in number 2, you now have a diol, 2 alcohol groups, and so they can each do the same thing. So this carbon is going to lose an OH, and that means its next door carbon, and there is only one to choose from this time, so there's no complication there. That one will lose a hydrogen. So in a first step, if just that one reacts, you will get this. But then this one can do the same thing. So the OH is lost from there, the hydrogen is lost from there, and so what you end up with is that compound. And of course, in this case, you've lost not just 1, but 2 waters. So when you're writing an equation, make sure you don't lose the 2 there, because organic equations have got to balance just like any other equation. Part 3, we have this compound. Again, it's probably helpful, at least I find it helpful, to redraw that in a skeletal format so that you can see clearly what's going on. So you've got the OH, and then the bond to this carbon, which is the CH2, and then that in turn is bonded to a carbon that has 3 methyl groups attached. So you get that. Okay, so that's the CH2 is this carbon, that carbon is this one, and then the 3 methyl groups around there. Notice, by the way, in both these formats, the way you write the OH group on the left hand side there. If you wrote it like this, or the analogous thing there, that is not acceptable, because it makes it look as if the carbon is bonded to the hydrogen rather than the oxygen. So when you have groups stuck on the left hand side of something, you have to be careful to write them in such a way that it's clear which atom is actually connected in, like that. So that's why I've drawn it like that. Okay, so if we try and then follow our recipe for dehydrating that, this carbon would lose its OH, and its only next door carbon is this one, and that would have to lose a hydrogen. But you can see the problem, that there is no hydrogen on there, because that carbon is bonded to 4 other carbons, so there's no room for any hydrogen. So the answer is that for that one, with the conch sulfuric in heat, there will be no reaction, because there is no hydrogen on the carbon adjacent to the one with OH. Okay, so most alcohols will dehydrate under these conditions, but in some cases, like that one, they won't, just because there is no hydrogen available, so the scheme that we've learnt for this reaction just can't apply. Right, number 4. Again, let's begin by writing it in a clearer format. So we've got CH3, CH2, and then this carbon has a methyl group and an OH attached. Okay, so the CH3 in brackets, remember, means it's a methyl group sticking off at the side. It's also got the OH there, and then you've got CH2, CH2, CH3. Okay, CH2 is there, CH2 is there, CH3 is there. So that's your skeletal formula. So this time we're going to the other end of the spectrum. This one couldn't find a hydrogen to eliminate. This one has an embarrassment of choices of hydrogens to eliminate along with the OH here, because you can see that if this is the carbon that's going to lose its OH, you've got 3 candidates for the adjacent carbon that could lose the hydrogen, and each of them does have hydrogens. So that gives you straight away 3 possibilities. So let's write those down. So conch sulfuric and heat. So if we lose the hydrogen from here, we're going to get a double bond there in between those 2 carbons. So that would give us this, and of course the OH has gone, so we've just got the methyl group remaining there. So that's one possible alkene. If we do it to this one, then we're going to get this. If this one is the carbon that's going to lose its hydrogen, we lose hydrogen from there, OH from there, so the double bond will come across here. So that can give us this product with the double bond now down there like that. So your first thought might be, okay, 3 possible products in that case. But in fact it's not even as simple as that, because when you're making an alkene, remember you have to consider the possibility of EZ isomers. Now in the earlier examples in part 1 and part 2 that didn't arise, because in both of those cases one of the 2 carbons that formed the double bond had 2 atoms the same attached to it, or 2 groups the same attached to it, and so EZ wasn't a possibility. But that's not always the case here, because you can see if we look at this one, that carbon has a methyl and a hydrogen. This carbon has a methyl and a propyl, so both of them have 2 different groups attached, and that means that EZ isomers are a possibility. And when you do an elimination reaction, you could in principle produce either the E or the Z, and in general you're going to get a mixture of both. So we have to write down the alternative isomers as well as further possible products of reaction. So the way to do that is, when you have one structure already drawn, the end that's more complicated, which obviously is this end, just draw that the same, like that, with the double bond here. And then the simpler end, you just draw that sticking in the opposite direction, so instead of sticking down there, it sticks up here. And so that's your structure. So those are one pair of EZ isomers. This one again, you can see this carbon has a methyl and an ethyl, so 2 different groups. This one has an ethyl and a hydrogen, so 2 different groups. So again, you can have 2 possibilities. So if we draw this end the same, So it's the same up to there, and then again the ethyl group, instead of being down alongside this one, it goes up alongside that one. And so you get that as your fourth possible product. This one, you can see has two hydrogens at this end of the double bond. So if that one flipped over, it would still be the same thing. So there is no EZ isomer in that case. So it's this, or this, or this, or this, or this. So in general, you're going to expect to get some kind of mixture of 5 different alkenes plus water in that reaction. So that's going to be something you want to avoid if you're doing synthesis, because you're going to get only a modest amount of any one of those, and if it's only one that you're interested in, that's going to be bad news. So part A in question 9 wants us to convert propan-2-ol, which is this, into 2-chloropropane, which is this. And again, that's a reaction you know, because we learnt that when we did haloalkanes as one of the ways to make haloalkanes. So the conditions for doing that are that you need sodium chloride plus concentrated sulfuric acid. So again, that's a specific reaction condition that you need to know. Again, you may want to heat it, but it's not an absolutely necessary requirement there. So if you just get the reagents, that would be fine. Sodium chloride plus concentrated sulfuric acid for turning an alcohol into a haloalkane. If it was a bromo one, obviously you would use sodium bromide. Part B asks us for an equation for that reaction. You can write this equation in various ways, but I think the best way to write it is to recognise that in effect what you're getting from this mixture is an H+ ion that comes from the conc sulfuric acid and a chloride ion that comes from the sodium chloride. So in effect you've got H+ and Cl-, and between them they will react with that and allow this substitution to happen. So it's a substitution because OH- comes out and Cl- goes in, so you get that product. And of course what that leaves is the H+ and the OH-, which combine to give you water. So I think that's probably the best way to write the equation, but commonly you'll see it just written as plus HCl. And the way of thinking about that is that this combination of substances makes HCl in the pot, and therefore overall it's the HCl that reacts. So you can write either of those as the equation. So question 10 is another synthesis question where it's asking us to transform one molecule into another in a way that you can't do in a single step. So we've got to put a sequence of reactions together, and again this one you can do in just 2 steps. So you can see there are basically 2 things we've got to do. We've got to transform that OH group into a bromine, and we know how to do that because that's effectively what we've just done in question 9. And we've got to take this alkene group and add across it to put a chlorine at each end. And again, that's a reaction you should know well from when we did alkene chemistry earlier on. So we can just do those 2 reactions in sequence. So probably doesn't really matter, certainly for A-level purposes it doesn't really matter. You always have to worry about which order should you do them in, because sometimes it will affect the outcome. And in real life it might well do, but for A-level purposes where we don't worry too much about complications that happen during reactions, I don't think it matters which way we do it. So let's do the substitution of the alcohol first of all. So what we're going to want to do is leave the alkene group as it is for the moment and put the bromine there. And that's very similar to the reaction in question 9. It's just a substitution of the OH in an alcohol with a halogen, and for that you need sodium bromide in this case and concentrated sulfuric acid. Okay, so that's the first step. And then we've got to turn our attention to the alkene, and we want a chlorine at each end of it. If we just wanted 1 chlorine we would add HCl, but because we want 2 chlorines we just react with Cl2. And no special conditions for that. So that's it in terms of what you need, and that would be all you need. It doesn't ask for equations, so you don't have to put them in. You just have to state the key conditions for each step. Question 11 wants an equation for the complete combustion of cyclohexanol, which is that. So the only thing that's tricky here is making sure you get the number of hydrogens right in the compound. So obviously you can sit there and count them, but actually with alcohols the easy way to do that is to realise that the only difference between an alcohol and an alkane is that you've stuck the extra oxygen in between the carbon and the hydrogen there in effect. So the number of hydrogens will be the same as in the corresponding alkane, and there'll just be one extra oxygen as well. Okay, so if we just had cyclohexane, which is that, you'd say, right, it's C6. And remember the rule is if it was an alkane, just a chain type molecule, it would be 2n plus 2, 2 6s is 12 plus 2 is 14. So it would be C6H14 if it was hexane, but for each ring you put in you have to take 2 hydrogens away to make the electrons available to close the ring up. So instead of C6H14 that would be C6H12. And so rather than count them, you can just say, right, well this is going to also have 12 hydrogens, but it's just also got that extra oxygen there inserted between the carbon and the hydrogen. So that compound is going to be C6H12O. And you're going to need that because you're going to need to know how many hydrogens there in order to make the equation balance. So it's going to be that plus however many O2s, and that's the bit we work out last, gives you 6 carbon dioxides, because we've got 6 carbons, and 6 waters, because you've got 12 hydrogens, which is 6 lots of 2, so 6H2O. So if we add that up, we've got 6 2s are 12 hydrogens, sorry, 12 oxygens there, plus another 6, so 18 oxygens altogether on the right, so we've got to have 18 on the left. And you just have to make sure that you notice that one of them is already there. So if you put 9 O2 there, it's probably because you forgot that that one was already there. So to get 18 altogether, it's that one plus 17 more, and 17 oxygen atoms is 8.5 O2, and that's your equation for complete combustion.